participants. And it is my great pleasure to present today's speaker, Gestur Ólafsson from Louisiana State University. He will be speaking about analytic continuation of Bergman spaces and commutative sister algebras. Please, Gestur.
Thank you very much. So I will try to be a little not too complicated. So what this will be kind of in 3 parts. So first of them will be the analytic continuation of the Bergman spaces, where we just focus on the ball, even if it is possible to do it more generally. A lot of that will also build on work by Brian Hall and his graduate student. Then I will talk about Toeplitz operator, and then actually connect everything with paper that I wrote with Matthew Dawson and Raoul some time ago, actually how to calculate the spectrum of the Toeplitz operator. Okay. So let us start with, the board. So this is just probably something that everyone knows here. We start with a measure, a probability measure on the unit ball in Cn. And the measure, this is the measure, and the constant Cn is chosen so that it is a probability measure. And then the Bergman space is
Bergman space,
sorry, is the space of holomorphic functions which are also square integrable. And this is actually a Hilbert space. Mm-hmm. Because what we will be doing later on also, then it is good to re-normalize it so, and let sigma be n plus 1 plus alpha. Mm-hmm. And now the Bergman space is defined for sigma greater than 1. Mm-hmm. And later on, actually, this will be the parameter that we use for the analytic continuation. And then it is well known, actually, that those monomials set to the beta, they are all in the Bergman space. And actually, every bounded holomorphic function is in the Bergman space because this is a probability measure. And the inner product can be calculated. That is just expressed in terms of, really in terms of beta function. Mm-hmm. And then we know that if we re-normalize it so that this phi sigma beta has norm 1, then we have an orthonormal basis. This is also a reproduction kernel space, which is also very well known. It's really the basic in the theory that this is a reproduction kernel and one can calculate it. One way to calculate it is to take this orthonormal basis, take the phi and phi conjugate, and just sum it all up, and then one get this reproduction kernel, which reminds a lot on actually the density in the measure. And this is, in fact, a positive definite kernel. And it's very common to actually think of this as a function of one variable and use the second variable just as an index. And then K sigma W is actually an element in the Bergman space and really generate the Bergman space. And also,
Gestur, don't you mix indices and the Bergman projection because you use both sigma and alpha?
Oh, that can be. I was trying to avoid that and realize that as everything from here on should be in terms of sigma. Because we have actually renormalized everything, and this is the connection now, so that you add the dimension plus 1, okay? And then, the orthogonal projection is the inner product with the reproduction kernel. You can write it this way here. that if you take the conjugation, complex conjugation of sigma, then that is just the same as flipping the order of the variable. Okay, and what comes out of this, and this is actually kind of a motivation, what will happen in a moment, is that one can think of this actually just as a L2 space, little L2, that because this is an orthonormal basis, then F is just this sum, inner product with phi alpha, then times phi alpha, and one can also write this easily in terms of the monomials, okay? So, and the norm is also the sum of the alpha beta squared times the gamma function that we had there, okay? So this is just telling us that if we define a density, omega W sigma, which is expressed in terms of the gamma function, then this Bergman space for sigma greater than n is just a little L2 of this with this weight. Okay?
Mm-hmm.
So if we...
Do you mean here greater than or equal to 0? For the
no,
weight?
sigma. This is also...
No. Before, you have W sigma beta, and then you have greater than or equal, and before.
The point.
The very beginning of the sentence.
Let omega... Oh, that is greater or equal to 0, yes.
Yeah.
This is a positive density.
Yes.
Okay, exactly. Sorry about that. I am always, even if I read it 2 or 3 times, I get people to read it over, there is always a typo that comes in. Okay, so looking at this, and this is actually an old story. I mean, this question about analytic continuation was already around 72. For all bounded domain, a lot of other people have worked on it, but somehow the idea that I will be using is this from the paper of Jan, 2000, and then actually Brian Hall and his student, 2009. And if you look at this, actually density, then this density is positive, easy to see that, and finite for all sigma greater than 0, okay?
Mm-hmm.
And that is the point then, okay? This little L2 space is well-defined, infinite dimensional Hilbert space for all sigma greater than 0. And for sigma greater than n, it is isomorphic to the Bergman space.
Mm-hmm.
And this kind of gives us the first kind of step, also first analytic continuation of the Bergman space. We have this Hilbert space, A2 sigma, isomorphic to little L2, and that space, little L2, actually has an analytic continuation for all sigma greater than 0, okay? But now the point is actually, if you have something in here, in the little L2, then you can actually sum this up, and you actually have something that is holomorphic, okay? That is kind of what we have up here for the space, and this actually tells you something actually about the gamma, that, okay, this is something that is finite, and we get actually a holomorphic function. And then if we define the inner product, those monomials are still then in this Hilbert space, and we define this inner product this way, then we can complete it, and we have a Hilbert space of holomorphic function. There is some working to prove that this is holomorphic, but that is really what we have in the first part. Okay, then we get the Hilbert space of holomorphic function, which is actually, again, isomorphic to the little L2 of W sigma. And those phi sigma that we had, this still forms a orthonormal basis, and it is a reproducing kernel Hilbert space, and the reproducing kernel is exactly the same. And I should maybe say something about that. In this first paper, actually 72, then what they did actually was to look at the reproducing kernel. They just classified the sigmas where this is a positive definite kernel. And if one has a positive definite kernel, then one has a Hilbert space. And that was kind of the main idea in the beginning. What is missing is that there is no measure and there is no projection in that sense. One can't.
So the result that capital F is holomorphic is from the later papers?
This you can just prove this actually by hand.
Okay.
By looking at actually the growth of the alpha beta. You can actually also kind of view this using a Laplace transform, but this is a holomorphic function. Okay?
Gestur, two observations, if you permit. First of all, it includes known spaces for different values of sigma, like Hardy space and
Yes.
Dirichlet space.
Yes, it includes all of them. One has to, I was actually going to do that, so one can actually exactly identify what sigma gives those spaces. If I remember right, I would really have to check it out. So sigma equals to n.
Mm-hmm.
I think that is the Hardy space.
Yes.
So
And for Dirichlet space, something sigma equal to n minus 1 or something like that.
something like that, yes. Yes.
And second, well, projections there exist because you have a Hilbert space and closed subspace, but it cannot be written as an integral operator.
No, that is correct. You can actually extend this definition, and but I mean the thing is that the Toeplitz operator are defined actually using this formula for the orthogonal projection.
Yeah, exactly.
And
yeah, sorry.
you cannot actually do that here.
Once with Rosenblum, we think about this problem, and as far as I remember, this reproducing kernel somehow is related to the so-called Lerch function, one of the special functions. If you sum up, like build it upon the basis.
Yes, I don't want to really comment on that because I'm not sure I remember exactly what the Lerch function is.
Mm-hmm.
But
never mind, it's somehow connected.
Yes, this is all, I mean, connected to a lot of special function, and also, I mean, Jordan algebra, this can be actually used by Jordan algebra and special orthogonal polynomials and things like that. There's a lot one can really spend the mathematical life just studying this function and related topics. This is a very kind of interesting topic. Also, if one leaves the ball and start to look at other domains. Okay, so let us actually look at that. So this is kind of what I follow here is mostly the ball by Brian Hall and his student, but I say also Clerc in France, and a lot of other people have done similar thing for other domain. And this Jan, also he did it for all the domain, also using Jordan algebra. But this is really actually what fits for what we are doing. One, okay, there is a missing set here, actually, that ended up an index. So one looked at the Euler operator on the ball and its conjugate. And one should remember also the conjugate actually kills all holomorphic function. And then actually it's well known if you have a homogeneous polynomial, then it is an eigenfunction of the Euler operator, and the eigenvalue is the degree. Okay, in particular, all of those monomials are eigenfunction, and the eigenvalue is better. And that actually leads to, one can define actually this 1 plus 1 over sigma E. And then that is clearly also a eigenvector. But the point is, this is done so that one gets exactly the sigma plus beta over beta, because if we look back here, we have this gamma function. The gamma function satisfies, if you add 1 to it, then you get sigma plus gamma sigma, okay? And also here in this one, okay? And we see actually what you get if you move that up. This is the factor, okay?
Gestur, am I right? Am I right that this, your E bar, sometimes called a number operator?
That is also something called the number operator. For example, Brian Hall, he used the notation n. If you're thinking of in terms of quantum physics, this would be the number operator.
Okay.
It counts the degree, which is kind of the number.
Yeah.
So, but I just like more the classical kind of the Euler operator, and but you can call it the number operator also. So that is absolutely also, if you're looking at Fox space and things like that, so creation operator,
Yeah, exactly. Yeah.
and number operator that comes in there. Okay, so another thing also with this also is exactly if you move it over, so the inner product, we have here the sigma plus 1, and here we have the sigma. Okay, that is just because kind of what we have in here. Just to look at what the norm is in terms of the gamma function. Okay, and this is kind of, the next one is kind of what is the base of it. This is really a standard technique. If you are, what you really have here is a positive polynomial on the board raised to a certain power. And then one can actually prove that there is always a differential operator that moves the powers, okay? And in this case, it is actually possible just to write it down. And this is just a very simple exercise, that if you apply also now with the minus, and that was the one actually, you have sigma plus and sigma minus, okay? Then if you apply the sigma E minus, then you actually lower the power by exactly 1. And this is what Jan also did in more general and clear. That was exactly to determine actually a differential operator like this, that exactly moves this power. And that actually leads to the fact that if you have sigma which is greater than 1, then, and the functions are differentiable and bounded or derivative in L2, then you can calculate the inner product in the sigma plus 1, E plus of G, or apply that to F, and then you get the sigma product, so inner product in L2 on mu sigma. One way to do it is just to apply this, for example, to the monomials, and if it holds for all the monomials, it holds everywhere, okay? So this is also a simple exercise. This one here, number 1, is a very nice exercise. Okay, and this now leads to the following basic idea in this analytic continuation. We define a higher order differential operator just by moving it up, because if you want to do this again, you would have to apply this operator again, but now with a sigma plus 1. Okay, and you can do this as many times as you want to. Okay. And this leads then to the following. We don't really need so much the first part, that if F is in A2 sigma, if and only if also certain derivatives are in there, And if you have two functions in the Bergman space, then you can calculate the inner product by applying those differential operator. And one should kind of bear this in mind. If you combine those two operators, you get just exactly this operator that moves the power up, but you can split it also up this way. Then this is the inner product also, and now you have actually a bigger sigma. And what is important is, so this also tells you that it does not matter what m actually you take. It is completely independent of the m. You can take whatever m is, you will always get this because the left-hand side just stays the same. And this is kind of then what one can use as a motivation, how to define the analytic continuation. Okay, so if you take any sigma greater, I mean, this is how they formulated, but as I say, so this was already known 72, so this is an old result, but this is how they did it. And I think they were the first one to use exactly this explicit operator, although if one can say it is maybe implicit in the work by Young. Okay, you take any sigma which is positive, and because of this moving up here, so the idea is just move the sigma so that this sigma plus 2m is greater than n. Then the left-hand side is well defined. Okay, and that is what we do. We take holomorphic function such that the derivatives are always in the Bergman space, and then we define the inner product this way. Because we know if sigma is big enough, this is the good old inner product. And this is a formula then that is valid for all sigma positive, and this is completely independent of whatever m you take, because if you take some bigger one, then you use just the previous result that you can add to this m, and you will always get the same thing. And then also if you take all the holomorphic function such that this holds, or you say this inner product is finite, then you get a Hilbert space of holomorphic function, which is isomorphic to the previous defined A2 sigma. Okay? One way to see the isomorphism is you just apply this also to the monomial, and you calculate the norm of those, and you see this is exactly the same as before, and if it is for the orthonormal basis, then it is for all of them. Okay, so this does not depend on n. And this is now actually what can be used to define Toeplitz operator. Let me somehow, okay. So as we know also the Toeplitz operator are for sigma greater than n. They are defined by this orthogonal projection, which is also just the inner product and kind of the integral where you multiply with f and take the reproduction kernel. And this is a bounded operator. It is linear. The norm is bounded by the norm of phi. And what is also important here is that the map, where you keep everything fixed except the sigma, then it's very easy to see this is an analytic map. Okay. So we have this analytic map, and then now surely the question is how to define this for sigma greater than 0. And that is again now surely one kind of know that from general principle, but this is also something that is used for Okay, you apply your favorite differential operator, but now one has to kind of always assume that the function has some derivative. And okay, so we just talked about this first one. And that means if we have sigma big enough and the phi is differentiable, okay, what do? You calculate the sigma plus 1 and the sigma, and you know that you can apply this differential operator. And now what you just do is you move it over. You take adjunct. And you can do that by partial integration. What is important here is that those functions here, actually, they vanish on the boundary. So there are no constant terms that actually show up, because this will always give you 0. So now you have actually then moved the sigma up, and you have still nice function here on the left-hand side. And now you can iterate this and do it again and again and again. They commute, so you should maybe have done this. No, it's probably correct, yes. Okay. No, it should have been in the other direction, but that does not matter. Those differential operator commutes. Okay. And now you have a higher order differential operator, and you define the Toeplitz operator using this formula that we found here, and by applying this differential operator to phi, f, and k set, conjugated, okay? Now actually here, because you have a derivative, and so then using Leibniz rule, and f and k set is not a problem, but for the continuation, you have to assume that phi has enough derivatives. And how many derivatives is the order of the differential operator that tells you that. And then it should be a bounded function after you've done the differentiation. And what is important here also is that this operator is a rational function in sigma. So this is a holomorphic function in the sigma except at 0. It has a pole at 0. But that is also telling you, if you look at this expression and you keep the f and the z and the phi fixed, then as a function of sigma, this is an analytic expression. Okay, which is good, because if you have to prove something, you can just move it over to the nice domain where everything exists as an integral, and prove it there, and then say, okay, analytic continuation tells you it is always correct. Okay, and yes, we have to define also the space of 2m times differentiable function, and such that the derivative is bounded. And it is a number there actually that always works. Okay, you take the same m for all of them, because if you go 2m here, then you are in something bigger than m. Okay, and this number 2 is exactly what one just uses to define the Toeplitz operator for every sigma greater than 0. This has now a is well defined if it is differentiable often enough, and all the derivatives have to be bounded, because if you write it out, you get a linear combination of derivative of phi, f, and k. Okay, so this is then well defined, and we again get the analytic function in the sigma. And the definition is again also, because it is the good old definition for a big one, then the definition is independent of the m. One always have to somehow argue that. It is linear and it is bounded. And yes, I say also, this is the wrote that twice now, so this is analytic and bounded. This should really have been also the map set goes to this is analytic. Okay, so one of the things now that changed, and I mean, one kind of would absolutely expect that, is that it is bounded, but the bound is not the infinite norm of phi, or does not have to be that. It can happen to be it. For example, if sigma is big enough. And what they did, Hall and his co-author, they showed by taking a very simple function, just as the absolute value of z squared. And if for this function, there is no constant so that this is correct.
Oh, it's a very interesting example.
It's a very interesting, what is really interesting, it is how simple it is.
Yeah.
And this also kind of shows that also this inner product cannot be defined by a measure, because if one has a measure, then this has to be correct. Okay, so this is then the definition, and now let us, after we have defined what a Toeplitz operator is, and I should say also Engels has also done work on this and made a very general definition. There are several classes of functions that is good to work with. For example, if you have a function which has a compact support inside the board, then one can, for example, write this as an integral. Because if the symbol has a compact support, then this integral actually, what we have up here actually without the e, that clearly is finite, because everything is bounded in here. So for operator like that, or operator that, for example, van is fast enough on the boundary, so that the vanishing of the EW kind of take care of the singularity in the measure and that we get here also, then and the reproduction kernel also, then we might end up having something that converges. So sometimes there are nice classes that work. Okay, so no surprise. So now we start to do some representations here. I think I need to speed up a little. So we use, as always, the group SUN, 1, and those are matrices of this form. A is a matrix, D is just a complex number, and U and V are complex vectors. And one can really write the relation for this because it is the group that actually fixes this form. It's work on the board. What one actually do to figure out what the action is, one takes actually the board and project that into the projective space by putting one on probably the right end. The ball acts linear on the projective space, and that way one can actually just calculate what the action is by doing that on the projective space and moving back. Okay, it is transitive action. The ball, the group that fixes the base point is the orthogonal unitary group. That is A and D here. Those two vectors are 0. Okay, and then one defines a so-called multiplier. That is V inner product Z, or not inner product, that is the bilinear form that we have here. So therefore I wrote it with a big dot here, and then it is the D that we show up here. What is important, the only thing that matters in this is just the last row. Everything else does not really show up. And this one here is only really defined, okay, if you have an integer, it's always defined. But if you have a rational, you have to go to a finite covering. If it is irrational, you have to go to an infinite covering. That means you would get here for you UN, also that is the center on the diagonal matrices, that becomes the real line. And then one define a representation in this way. This is just a geometric action on the board, and then you multiply by the multiplier. And then what one shows also is this relation for the reproduction kernel. This is just exactly the same as showing that the representation is unitary. You can move it from the set into the W if you're taking the inner product, and it defines an irreducible and unitary representation acting on the Bergman space. Okay. What one also needs is the concept actually of intertwining operator, and that will play a role in a moment. Most of it is we just have one representation, and that will be, we look at subgroups of the unitary of the SU, n,1, and we just look at it as a restriction, as a representation of that group. Okay. Okay, so what is important is that if one has the same representation, okay, then you look at all the operator that comes from Python G, and then the intertwining operator, or just the commutator of that algebra or that set, and that is a von Neumann algebra. This is always a von Neumann algebra, and okay, so what one then shows is that for a big sigma, then this relation here is known, also that if you take your Toeplitz operator, you let the representation first act, and you are back in the Bergman space, you apply the Toeplitz operator, or you can do it the other way around, first the Toeplitz operator and then the representation. What comes out is actually you have to look at the action of the group on the symbol. This was proved in the paper that I wrote with Raul and Matthew, but later I've seen also there are a lot of people that have done similar things. Suarez, for example, it shows up in his work, and this is kind of very important relation that tells you exactly this action on the two different kind of action, the representation and the action on the symbol. And this is
you extend this for positive sigma. Suarez did it for big sigma.
He did it for big sigma, yes. This has, I think, never been looked at for the small sigma. This has never really come up there, actually. But what you simply do is you look at this for big sigma. You look at this map here. You can, if you want to apply it to F set, so you have a complex valued function.
Yeah.
And because this is for big sigma, correct, then you just take the analytic continuation, and it has to be correct for all of them. This is one expression of this very simple principle. Do it for the big sigma, and then take the analytic continuation. There is one thing here, actually, that what we use, this is kind of what is here, actually, that it is an intertwining operator if and only if the function phi is sigma, is invariant, but here we might have some extra zeros. I mean, one would have to make absolutely sure the map is injective to do that. Okay, this injectivity actually this was removed. I'm obviously not using the most recent version. I don't know why. Forget this first section. We never use that, and let us just move on. So what we are now doing actually is then also this paper with Matthew and Raul for 2015, and later we use those ideas for the maximal abelian group of SU n,1. And what also the rest of the talk is kind of all related to that extension of those results to the case sigma is greater than 0. Okay, so if you have any subgroup of the SU n comma 1, or you can take any group that acts there, also okay. And then you look at the invariant simple. That simply means this action here is just always B, as long as you take A in H. Okay. And look at the C star algebra generated by those simple. Then, because we know if you have an invariant simple, then the Toeplitz operator is intertwining. So that means that if the algebra of intertwining operator is abelian, and this is something that is studied a lot in representation theory, I would say this is almost, this intertwining operator are one of the fundamental problems that people look at in representation theory. So if this is abelian, then the Toeplitz algebra, there is a typo here also, is abelian. Okay, if H is compact, then it is if and only if. This was done in the paper with Rao and Matthew in 2015 for sigma greater than n. And that is actually the extension. And to extend this, one needs some simple remarks. And first of them is, if we take the space of homogeneous polynomial degree m, then they form an irreducible representation of the unitary group. And actually the Euler operator, which is actually used to do all the construction, is just m times the identity of the space. So that is telling us that the operator dm that we use, because that is just a product of 1 plus a rational function times e, actually commutes with the action of k. Okay? That you can kind of, if you have any subgroup that's in K, then you can differentiate and then take the average, or you can take the average and then differentiate. That is important here. And that actually, this averaging in the if and only if statement, there were kind of two things that really played the fundamental role. The first of them was that if you have a operator, then you can approximate it by Toeplitz operator. So if you have an intertwining operator, then you can approximate it by Toeplitz operator. You can repeat that proof and it still works in the general case. Exactly the same proof. Okay. And then the other argument, and that is the reason we can say if and only if for the compact case, you average it and show that you can approximate it by Toeplitz operator with invariant simple. And this kind of is telling you exactly the same thing. Okay, so this is the other part actually, that because what we have here in the definition of Toeplitz operator, okay, that is where this operator here actually shows up. That is the definition. And what this is kind of telling you, that the averaging commutes with those differentiations. Okay, so that can all be repeated. Okay. So the last thing then actually is the well-known things that people have, okay, two people here in the audience, they have studied the maximal abelian subgroup in SU n comma 1 and showed that all of them, they lead to abelian C-star algebras. The invariant simple give you commuting Toeplitz algebra, and also they showed actually how to do the calculate actually the spectrum of those operators, because if you have a commuting C-star algebra, then you want to know exactly what the spectrum of those operator is. And then we did actually in 2018 by using the same ideas as in 2015 paper, actually the so-called restriction principle. That is by taking holomorphic function and restrict that down to an orbit of this group H, multiplied by certain density so that this becomes a nice intertwining operator, and then one can use the analysis on the smaller group to study the spectrum, and in particular, if it is a abelian group, then one has a very natural Fourier transform on those abelian groups. Okay, that is kind of the idea. So let me just say a few things, and first actually, so this is not always needed. So let us just look for a moment on the compact torus. This is one of them. So those are the diagonal matrices. Remember also the SUN was a big matrix A, and then something D. And what one has on the diagonal is AT1, AT2, etc. That is what we have here, and then it is in the D is the A. And remember also the A here is always the things that kind of showed up in the J, in construction of A. Okay, to actually define all of this, one has to go to the universal covering group and what happened there. Okay, that is one takes this parameter here and makes that into something real. And then this relation becomes this relation here with the exponential function. Okay. So I don't know what this is probably, so this is invariant, and okay, yes. So what is important here actually, if you have a T-phi actually, that if you have any kind of intertwining operator for the total action, the polynomial, the standard orthonormal basis, this is an eigenfunction, it's an eigenvector, and so this acts just by a multiplication. So every operator is just this way here.
We cannot hear you, Gestur.
You don't hear me?
I hear fine.
Yes, so I don't see any problem. You still hear me, Matthew?
Yes, I still hear you fine.
Okay. So this what we have here, those are just the eigenvalues. Okay. So one does not need any kind of fancy theory here. So if you have sigma is big enough, you can actually calculate those eigenvalues as an integral, and then you use analytic continuation. So if you know the eigenvalues for big sigma, you know that because this expression here is analytic in sigma. I should have written sigma up here. So if you have calculated this integral for big sigma, then you don't have to worry about how the inner product is defined anymore. You just use the analytic continuation. So this is one way to do it, but we will do it in a different way in a moment. So here is kind of the idea that we wrote 2018, many years ago, that you've tried to find a point where the orbit map has the property, this is now a manifold in the Bohr, that it has to satisfy a so-called restriction injective. You restrict the holomorphic function on it, then it is zero if and only if f is zero. So, for example, if you have some kind of the situation is really also related also to symplectic geometry. This is like if you have a Cn, you have just Rn sitting in there, and that is the typical example. But there are a lot of other cases. It can both be bigger and it can even be smaller. Okay, there are points actually where you have discrete sets even that this is satisfied. Then you look at this d sigma or d8 sigma, that is just this co-cycle, and you fix the second element, and then actually this is a homomorphism if you look at the stabilizer, because J of AB comma Z is the same as JA B comma Z times JB Z. And if the element fixes the Z0, then you just have the product, and it's a homomorphism. There is just a reason to put in here the inverse, that is kind of the definition of line bundle. Okay, and then because it is a homomorphism, one can look at a line bundle over this orbit, and this D is always a section, okay? And the condition that one always need is that this function is a L2 section, okay? So this is a function that satisfies this covariance from the right, and because of this unitary character, then this one here does not depends on the centralizer. So this is just an integral over this quotient. And in the case of the maximal abelian group, this is just a abelian group. And one knows the L2 of that abelian group, and one has a Fourier transform on that group. And then the restriction is done exactly so, that you restrict, and then you multiply by this D, because then on this space you have the standard left translation, and then you have the representation on the big space, and this is an intertwining operator. So everything that tells us about how H acts on this Bergman space, that can be calculated in this much smaller L2 space. Well, not smaller, it is the same size, but it lives on a smaller group, and L2 theory on abelian group, for example, is well known, okay? And then we just close it up. Usually this is not all of L2, because we are looking at holomorphic polynomial, not all of them. So just a holomorphic polynomial, so this is usually much smaller than L2. And then we have actually a densely defined operator here, and we can take the polar decomposition. Okay, and this is a unitary isomorphic between the image and the Bergman space, or if you want, U star is a isomorphic, unitary isomorphism A2 to the image. Okay, so that allows us to do just abelian harmonic analysis to calculate things. The problem is that this U is usually not easy to figure out. What is also important is that this R star sigma, it is always a convolution map. That comes from the reproduction kernel, and as we see here, it does absolutely not matter how this inner product is defined. This is always true, this is always true, and this is always true as long as we are in L2. So this form of the R sigma star is always correct, and this is then, as long as d sigma is in L2, then this is always a convolution. So what one calculates is, okay, the U is the unitary isomorphism. Okay, so if you can kind of diagonalize the left-hand side here, then you have actually done your homework. And what the thing is, U is complicated, R is easy. It is a convolution operator. And everything is included in this one expression here that you can calculate for your error. That simply means it's a convolution operator with the square root of what you get here. And then you take the abelian Fourier transform, it's a multiplication operator. Okay? So you can actually calculate this in all cases. And if you take the Toeplitz operator, you get exactly the same formula, except you have here actually this inner product that kind of only involves the reproducing kernel, okay? And then you have a convolution with this function, and again, to find the spectral decomposition, take the abelian Fourier transform, okay? And what is important here in all of this, it does not matter how we define the inner product on the space in the beginning, okay? It is all about just, okay, the inner product comes out in here for sure, actually, that is not a question. But phi defines a Toeplitz operator everywhere, so one can calculate this for big sigma and use the analytic continuation. Okay, so let us look back at this just to really see how this works. Okay, so we start with the torus, and this would, you can take a lot of points, but this is one of them. Okay. And you take this orbit, which is just an isomorphic to the torus. You calculate the function, and just remember, it is always the bottom d that plays a role there. Okay, so this is what you get, just the exponential function. Okay, and the function that you are convoluting with is just this simple function here. And this is a, you see, the orbit that we get, okay, is just the torus. This is the one actually that lies in the stabilizer. So if you take the norm, this disappears. You only get kind of something that depends on the t, continuous function. It is definitive L2 function for whatever sigma you take, okay? So you always end in the L2 space, okay? This is then the representation on the sections. And what we see here, this is just the multiplication by sigma, easy to deal with. This is just the standard action of the torus, okay? And then actually, if you look at then the restriction, you can, so to say, take your line bundle that we have in the definition, and this is a trivial line bundle. It is the L2 of the torus times just the C, okay? And that is the C here, so this center, this X part, just acts by the multiplication, and the torus is just the usual action of the torus, okay? And what you get in here is kind of all the function that if you look at the Fourier expansion and the t variable, all the negative coefficients disappear and you just get the Hardy space. And then you can use your formula to calculate the spectrum. Okay, and then it is the quasi-parabolic. And what happens now is you have in the beginning the torus, and then you get something that actually kind of lies in the SU11. You get a matrix. And what you get extra in this one is you get a parameter that is in the real number. Okay? So now the things becomes a little more complicated. The torus, again, is not a problem. Okay, and so here is the point. Take just a 0 here, and you look at the action of this group. Okay, this is very similar to what you would get if you're just working SU11. And what we see is you get the y in here and y, and then the torus, and you calculate your function. Okay, For the universal covering, you would have to extend this A. That does not really matter then. You split the line bundle again up. You have the sigma here. Okay, that is what comes from the A. And then you have 2 minus I y. And that is only integrable if sigma is greater than 1/2. Okay? So this is not in the L2 for all of the sigma parameter. You have to stop as you hit the 1/2, but that is easy to deal with, okay? And you just take this one operator, the partial derivative, you differentiate it and you move the parameter. It is exactly the same trick again, except this is much easier, okay? So now you have something that is valid for all sigma greater than -1/2. And then you define your restriction, so you restrict your function, and then you differentiate, okay? And then you get something that is in L2. Okay, and what is important here actually, because you want to use the representation theory, in the first piece, you can move the representation pi over here. Then you just get the translation. That is what the action is. And this is a constant coefficient differential operator, commutes with the translation. So this again is an intertwining operator. And what we are kind of looking at is some kind of Sobolev space. You could actually, in fact, use the delta, the just Laplacian to do it, and you would have moved it by 2, and then you get also really a good old Sobolev space. And what that makes sense, one of the reasons, this is the square root of the Laplacian. So this would be a Sobolev space H1/2 or something. Okay. And that then means, actually, again, we can play the game and get everything working. And you can do it for all the other cases. So let me just see what happens here always as you move on. You get a bigger space here with the realm. You start to get a vector, okay? Otherwise, this D is always something that involves the Y. Just actually more variable. And what do? You do the same. You use partial differentiation, okay, to move the power. So you can again do everything. And what is important is the partial differentiation commutes with the translation. So you can always use this restriction to calculate then the spectrum. And okay, I wrote down here actually what the sigma is for those different cases. This tells you also how many differentiation you have to do. Okay, I think I just stop here also, and I have been also 1 hour or more than that, so I guess I did talk a little too long.
Okay, Gestur, thank you very much. It was indeed a very interesting talk.
Thank you.
So please, questions, comments, or whatever to the Gestur talk.
I have a question. This is a silly question, but is there a non-trivial Wallach set in this case?
The endpoint is actually Wallach set also, but it might be also that you just get a trivial representation, I would have to think.
Okay.
Just look at the case SU11. Then actually you get also one endpoint there. And
Right.
I should know it, but I mean, I cannot say it exactly just like that. Also. But there is a Wallach set. But it might just consist of the trivial representation. I would really have to check on that. What he is saying is you do this analytic continuation, and then you have this continuous parameter, and then there is a point where it all breaks down, and it is not positive definite anymore, but there are certain equidistance points where it is still positive definite. One can actually see this also, I think probably a good example. My example did not work. But that is what actually the Wallach set is, the continuous one, and then those discrete point, because it was Wallach, Nolan Wallach, that realized this fact actually first.
Okay. More questions or comments?
I have one question
about
the spaces.
Okay.
You work in some spaces where the inner product cannot be written as the integral of the type L2 with respect to some measure. Yeah.
Measure on the board. There are some cases where you can actually kind of find a measure on the boundary. For example, the Hardy space, there is a measure on the boundary that kind of gives you the Hilbert space. But on the board, there is no measure.
Well, on the original domain where this is reproducing kernel Hilbert space. Yeah.
Yes.
Well, the question is, if it is possible to prove it formally that there does not exist such measure.
There is a lot of, I would really have to check on that again. Actually, there is a lot of work on that. What do you mean formally?
Well, a true rigorous proof that there does not exist measure such that the inner product can be written as the integral.
There are proof like that. I mean, there is this proof, for example, in the
even for the Hardy space. Have you found?
No, I have not also, but what actually, I mean, the proof that Brian Horn gives is exactly this, that if there was a measure that gives the inner product, then you would still have also that the Toeplitz operator, the norm of the Toeplitz operator is bounded by the norm of the function.
Mm-hmm.
Oh.
Yes, and that is not the case because you have a counterexample.
Excellent idea.
Yes.
Thank you.
Gestur, maybe another approach that it should be analytic with respect to parameter sigma. And this is moving sigma down. We have some kind of obstacle to be analytically continued.
That is probably also possible, yeah. I mean, it is always a non-trivial, it is sometimes easier to prove that something exists than show that something does not exist.
Yes.
One really has to find a good example for that. But I think actually this idea about that the norm is not bounded, actually that should probably work in all cases. But this is a very nice idea.
Yes, it's very straightforward.
Yes, and this is done in this paper actually.
Well, this means that you are right. Here it is not important if the measure is bounded or not.
No, if it was given by a measure, also you just look at this. This is the multiplication operator on the big space, and we know that that big space is the multiplication operator is bound by the norm.
Yes, exactly. Yeah.
and then you project it down, and then the norm becomes never bigger. Yeah. So this is a very nice and a simple idea to prove it in this case.
As long as it's a regular measure that's absolutely continuous with respect to the Lebesgue measure, right? Because otherwise the L infinity norm would be different if you're no longer considering measures that are absolutely continuous with respect to Lebesgue measure.
Yes, but can it actually become bigger? Oh, yeah.
Well, I guess then it might not even make sense to define it for. Huh.
I mean, every time you have a L2 space and you look at this and the space, smaller spaces contained in there, you have this projection mechanism. And this multiplication operator is always bounded because the L2 spaces, whatever the measure is, has the property that if you multiply by a bounded function, then phi f is in the L2 space, and the norm, L2 norm, is less than or equals to the infinity norm of phi. That's always the case. So that has nothing to do with the regularity.
Well, a technical condition is that in the example, the generating symbol is continuous in the usual sense, and this usual continuity have to imply the measurability. So the measure.
That's great. Yeah, and that would and it's in that case it's in L infinity norm would definitely have to be its maximum, and so there. Or there's only one possible. There's only one possible L infinity norm in that case for this phi, which was the absolute value of z squared, right?
It is natural to assume that the measure is the sigma algebra contains the Borel sets. Yeah.
Mm-hmm.
Yeah, I don't know. I mean, you would just have to assume actually that all the holomorphic functions are measurable with respect. Yes, that would imply they are. The sigma algebra contains the open set. Yeah.
Oh yeah,
yeah. That's enough.
Okay. If there is no more question, let's.
May I ask one more?
Yeah,
Sure.
of course.
So how much of this have you pushed through to the higher ranked domains? Because I imagine that.
Not also really done that, but if one looks at this paper for 2000, where he actually, Jan did kind of exactly the same thing by constructing a differential operator that moved the parameter. What he used is actually the realization actually with Jordan algebra. Then it is related to the Jordan determinant and all of that. So one can say this is relatively concrete. And there is also, I would maybe think that might even be more readable. There are some work by Claire that you also have those shift operator. And I think you can actually, if you want to become quite explicit, but I have not really done that. It is an interesting project actually to do it, and I am quite sure actually that one should be able to.
Okay, Gestur, thank you very much for a very interesting talk.
Okay.
You are always welcome to our seminar.
Thank you.
And next.
We do not hear you, Nikolai.
I think he's having problems again.
Yeah.
So I I think he wanted to say that next speaker is Jesús next week.
Yes.
So I will send the information at the end of this week. And thank you very much, Professor Ólafsson, for your talk.
Yeah, thank you for hosting me. Okay, thank you.
Thank you.
Bye.